I'm going to be talking about some work I did with Wei Jing while she was a PhD student in China. She visited me in Waterloo for a year, and we worked on a few projects on geometric algebra, and this is one of those projects. What we're trying to do is ray trace tori, and I'll talk a bit about ray tracing in a bit. And so that we were working in the double conformal model because we needed representation of tori. So we're looking at working with the line Cyclide intersection. And along the way, we investigated what we call collinear point quadruples. So I'm assuming most of you are familiar with the conformal model. So I'll just briefly touch on a couple points. Right, we have our Euclidean vectors, a point at the origin, a point at infinity, or alternative basis representation. Points in this model are represented as an offset from the origin plus a term at infinity. And one of the things this gives us is if we take the inner product of 2 points, the result is proportional to the square of the distance between the 2 points. So in this talk, we're interested in a double conformal model, and it's pretty much like it sounds. It's 2 copies of the conformal model. And most of what I'll talk about is about the double conformal model is the work of Easter and Hitzer. So we have our 2 copies. They have their set of Euclidean vectors. Each has a point at the origin, a point at infinity. But the double conformal model also has its own point at the origin and point at infinity. It's just the outer product of the 2 points at the origin and the outer product of the 2 points of infinity. And then we define points in the double conformal model just by taking the same offset vector in each of the 2 conformal geometries to construct the points. And then the outer product of those 2 points is a point in the double conformal model. And now when we take the inner product between 2 points, what we get is proportional to the 4th power of the distance. And very loosely and informally, it's this square in the conformal model that is giving us these quadratic surfaces in the conformal model, and it's this power 4 that's giving us these quartic surfaces in the double conformal model. Very, very informally there. And then we can represent lots of objects in this geometry. I'll say lines and planes are represented in a fairly standard way. You just represent them in the conformal models, the 2 conformal models, and take their outer product. I'll talk about higher degree surfaces on the next slide. And of course, you intersect things by taking the outer product, with the caveat that if your intersection is not representable as a degree 4, then you get 0. Right? And so the way that we represent our quartic surfaces is we have these bivector extraction operators. So as an example, if we have an algebraic equation for a torus where t is our query point, then wherever we have t to the 4th in the equation, we just look up t subscripted t to the 4th here, and that will be a term in our double conformal representation of the torus. So we set all that together, and this is a representation of the torus in the sense that if we have a query point and we take its inner product with our double conformal torus, this is 0 if and only if the point is on the torus. And what we're interested in is ray tracing tori. So in the review for the paper, one of the reviewers wanted me to say more about ray tracing in the paper, but it seemed like I pushed off the ray tracing to other references, but I thought I would give a brief summary of ray tracing for people here who aren't familiar with it. Basically, it's a method in computer graphics to generate images for a scene. And all a scene is a bunch of objects positioned in your world. So down here, my scene is this sphere, this cube, and this torus, plus a light source. And then you locate the viewer, so an eye point position in the scene, you're looking in a particular direction, and then you have your image at some arbitrary distance away. And then for each pixel in your image, you cast a ray into the scene, and then you intersect this ray with all of your objects in the scene, giving these cyan points, okay? And we're interested in the intersection point that's closest to the eye. And so usually when you compute these intersections, it's there's a parametric equation for the ray. So you're looking for the smallest positive t value for that intersection point. And at this point, we're going to perform a lighting calculation to see how much light from this light source reaches this point on the, reflects off this point in the torus back to the eye. Okay, and usually this, in the sort of simplest ways of computing the color, you cast a ray to the light and you use the normal here to compute the intensity back to the eye, and that gives you the color of the pixel there. Okay. And then you repeat this for all the pixels in your image, and that's how you get your picture. Okay. So what we're interested in this talk is how do we get these cyan points? How do we intersect this ray with the torus? Now, on one hand, Eastern hits have already done this for us, right? Because the intersection of the torus and the line is just the outer product. But what this gives us is what Wei-Jing and I eventually called collinear point quadruples. It's an object where if you take a query point and the inner product of this thing, you get 0 if and only if this query point is one of your 4 points of intersection. But we need those 4 points, right? It's not enough to say we can query and decide if a point is on one of those 4 points or not. So how do we compute these 4 points of intersection? Now, we're implementing all this. We eventually had a fairly coordinate-based approach. This is where things got a bit unsatisfying in working in the double conformal model, because we don't really have good ways to construct the rays, right? We wanted to have a point plus a linearly parameterized vector, but there's no real way that I know to do this in the double conformal model. So essentially, we extract the coordinates of the direction of the line, and we have a point on the line. So with coordinates x0, y0, z0, these are fairly easy to get because we know where the eye is. We know the direction we're looking. They're not too hard to compute. And then we construct our ray in coordinate form as x0 plus t times the direction in the x, and do the same for y and z. And this point is on the intersection of line and torus if and only if this inner product is 0. So all we have to do is expand this. This is an equation in T, and you get something like 100 terms with duplicates, which I reduced to 89. You can probably reduce it a bit more. And I'm trying to type this in, and I decided I didn't want to type in 100 terms and debug it. Okay. Yeah, I could have got Maple or Mathematica to dump out some code, but I like the program, and that feels like cheating. Okay. So what we did instead was we used the fact that, right, the point in the double conformal model is the outer product of 2 conformal points, and each conformal point has this representation here. And when we plug, right, our equation into here, we get a quadratic equation in T. And so it's, you know, the K, M, and N are the constant, linear, and quadratic coefficients, and similar for the other conformal model. Okay. And so now when we do this expansion, this expands nicely into things that I can actually program. And of course, I had to type all these in. So again, it's not too bad. And then everything here is grade 2. So these are all scalar values. We have a degree 4 equation in T. So we just solve for the roots and substitute the values of T into this equation to get our 4 points of intersection. In ray tracing, we're often interested in just the first point of intersection. So you can just choose the T value, the smallest positive T value, and only substitute 1 into here. Okay. And of course, there might not be any row roots because you might miss the torus and things like that. Yeah, you can handle all those details. It's fairly standard. So that's pretty much what we did to do the ray intersect torus. The only thing I'll comment on is we also do quadratic surfaces, and you can use the same equation here. It's just that you know these will be 0, right? So if you know you have a quadratic surface, then you don't compute the cubic and quartic terms because a priori you know they're 0, and then you only have to solve a quadratic equation rather than a degree 4 equation, and you don't have to worry about what if these things are close to zero because of numerical issues? And in ray tracing, we almost always know if we have, it's a sphere or it's a torus, so we know what the degree of the surface is. So that was fairly straightforward, but we decided to look a little bit more at the collinear point quadruples. So if we do ray intersect cyclide, that's what we get back, assuming that the ray hits the cyclide. But we decided to ask the other questions. Suppose I have 4 collinear points. Can I construct that collinear point quadruple directly? I mean, we didn't want to take our 4 points, construct a torus that those 4 points lie on, and then intersect them. That'd just be crazy. So we derived an equation. So if we have 4 DCGA points with a side condition, I'll talk about a little bit more later, then this equation here, where we're taking the point at the origin, the point at infinity, in each of our 2 conformal subalgebras, and the inner product with the outer product of the, we're taking the inner product of these with the outer product of the first 2 points and the last 2 points, then this basically gives us a dual of the collinear point quadruple. So it's 0 if and only if these is one of the query point is one of the points, the original 4 points. So a few notes on this. Weijing re-expressed this in this form. And the main thing of interest, so this is algebraically the same. You expand these, you get the exact same equation as we did before. But we have these coefficients here. And this is just the sum of the squares of the coefficients of each of our 4 points we constructed with. And this, if we have, right, that's the reason we have these side conditions, because we have equality here, then this collapses to 0. So the construction is coordinate system dependent, because if you have these conditions, you have equality here in one coordinate system. If you were to change coordinate systems, then that's almost definitely not going to be the case anymore. So it is what it is. Maybe it's not ideal, but it is what it is. And I wouldn't be surprised if a lot of our equations have, if you go to implement them, have some coordinate system dependencies at times, okay? The other thing is that this is not a unique representation of collinear point quadruples. In particular, if you intersect a ray of a torus, where you actually get an intersection of 4 points, that is a collinear point quadruple. You then take those 4 points and you construct the collinear point quadruple using this equation, and you normalize them and take their difference. It's a non-zero difference between the one that was directly a ray intersect torus and the one we constructed with this equation. So there's this sort of null space out there of this other stuff, which we didn't really investigate, we just observed it. Then we asked the sort of the opposite question. If you start with a collinear point quadruple, can you extract the 4? Can you find the 4 points from just the collinear point quadruple? And what that really boils down to is, can you find the line they lie upon, right? Because if you can find that line, then you can use the equation we had earlier. We have some partial results there where if the collinear point quadruple was computed using this equation, then we're able to extract the direction of the line. And using this equation, we get a sphere that passes to the origin, whose center is a point on the line. So you just invert the point at infinity, you get the point on the line that way. So we could do this. So a few geometric algebra ray tracing details. We implemented these, but they're not original with us. When you write a ray tracer, you often have your objects sort of in canonical position, then you transform them into where you want them in ray tracing. And we just use the transformations that Easter and Hitzer did for the double conformal geometry. Shading requires normals, and this is, again, is in Easter Hitzer's paper, but some of these papers are very long, and when I was trying to find them, I had trouble finding those equations, and Weijing pointed me to this other paper, and I just used their equations for the normals. It worked fine, but I'm sure Easter and Hitzer's would also work. And finally, we could ray trace triangles, and the way you do the shading, you need barycentric coordinates. So I just used the formula for barycentric coordinates in the conformal geometric algebra representation from the book that Leo and I wrote. And that's pretty much it. In conclusion, we could ray trace in DCGA, we could ray trace tori. It was a bit coordinate system heavy. That's kind of my critique of our method, but that's just what it is. The main issue, of course, is that there's no direction vectors in DCGA, so we couldn't construct those rays, and that made us pop into coordinates at times that I didn't want to. But of course, you're unlikely to find ray intersect cyclide without solving a coordinate equation, however you do it. I just can't see not getting around that some way. And we can build these collinear point quadruples directly, but there's still some open questions there. And if for some reason you think, gee, this looks like it's pretty straightforward, I have a library for double conformal geometry, I'll just hand it off to undergrad, and a week later they'll give me back a ray tracer. No, that's not going to happen, because there are lots and lots of additional details you need to get a ray tracer to work that I didn't talk about here because they're not geometric algebra related. It's a bit more complicated process than I described. And finally, don't get up yet. So finally, we can understand the picture ray trace. So here we have our basis vectors for the one of our conformal geometries with the origin point at infinity representation. And here's the other conformal geometry. Their outer product is the double conformal geometry. We have our cyclide and a line intersecting it in the 4 points, a couple more cyclides, and back here is our G82. And this is Wei Jing's last name, Yao, in Chinese. So that's it. Thank you.
Thank you very much. Are there any questions?
Hi, Anthony Lazenby here. So it's a bit worrying about the coordinate system dependence. So I wanted to ask about the covariance of the double conformal model generally. Presumably, all the operations are covariant, and therefore not coordinate system dependent if you apply the same rotor in the 5D space to each of the two copies. Is that true? And does that give a way through to what you're doing, but not being reliant on coordinate systems?
So the short answer is I don't actually know, but part of the reason I did things in coordinates is because we are implementing it on the computer and those coordinates are right there. And often when you have coordinates, the temptation to use them is pretty great, especially when you're trying to make things run fast. Because shall we say this was slow, okay? Because the algebra is fairly high dimensions. So for example, I sped it up by putting in bounding boxes, and the bounding boxes were completely coordinate system. So, but I don't know if there's ways to get around some of these things. It would have been nicer, right? I would have been happier if we didn't have all the coordinate system dependency. But again, a lot of that came out of just the fact that we were coding it up as we went along and drive things. So,
Leo?
Yeah, Leo Dorst here. So what level of student was this? I tried to get an impression of how easy it is for people who have not been educated in geometric algebra to grab some of the structure. You obviously did some further development.
What level is Wei Jing?
Yeah.
She's a PhD student in mechanical engineering, and her supervisor does work with geometric algebra.
Okay, so she had prior knowledge.
She had prior knowledge. So,
okay.
So you can't, sorry, there's no.
No, but you clearly had to do some further developments to embed this particular.
Say that again?
Exploit. You had to make some further developments to exploit the structure of the thing that you were looking for, and it looked fairly advanced and not something that is standard.
I actually did most of the coding. So when I say most, I mean all. And
so you got 2 PhDs now.
She did a lot of the math. Okay, but every now and then she gets stuck, and I would say, well, let's just try a couple of things. I'd code it up, and the answer would pop out almost immediately, which it makes me look really good to her. But I'm thinking, well, that was lucky, right? So yeah, I would help her with the math when she got stuck, and I would just kind of blunder my way into the right direction because I have enough experience, right, with the geometric algebras that, you know, if I kind of walk in a random direction, it's not so random. Right?
Yeah. So my question is how teachable is something like this, or how generalizable would it to be as a method to approach imaging a certain class of objects, or is that not clear yet?
I mean, a lot of the concepts are straightforward, right? You're doing ray-intersect objects, you get these equations. It's when you start to poke down in the details. When we were exploring the collinear point quadruples, right, that's really when she was doing it. She did all the math there. I think that possibly I did something right. So she actually, right, knew how to do the math. It was fairly advanced, so I don't think it's something that's very low level, but it was all new stuff, right, that she was developing.
Yeah, I remember that when we tried to, point pairs are a basic primitive in CGA, and it took a bit of work to get the points back from the point pair because it was not a natural question to ask of CGA, and that's of course one level deeper here. Yeah.
So I pointed her to that equation, and then she came up with the other equation. So she knew how to do certain things pretty well. I give that credit to her.
So can you extend this in the direction you're going and use triple conformal models to use a triple conformal model to expand your primitives, let's say?
Oh, so Eastern Hitzer talk about this in one of their papers, and each time you add another conformal model, you get 2 more degrees in your surfaces. So if you had a triple conformal model, you get degree 6. You had quadruples.
Are they useful in modeling?
I haven't looked at them, and they didn't look at them either. They just pointed it out because Ron Goldman and I were looking at this paper and said, gee, I wonder, can we write the sequence of papers, the triple, quadruple, and so forth? But then we noticed in their conclusions, they mentioned this, and so they wiped out the sequence of papers we were going to write.
Yeah.
I'm not really sure whether we already have this triple conformal model available in a publication. I'm not sure. Okay, other questions? This is not the case. So thanks again, Stephen, for your very nice presentation.